Hello, this is Gabe Rogers. I'm doing motion of a falling object, lab 2. The purpose of this lab is to observe an object drop from rest that falls straight down slower than if it were in free fall. Our objective is to record and model the effects of drag by a force against the direction of motion and whose magnitude is proportional to the square of the object's speed. So we will be using turbulent drag for this lab. The concept is Newton's second law, and we'll be using the which is force equals mass times acceleration. And we'll be using the position and velocity update formulas, gravitational force, and drag force. And for this drag force, we're using B, which is a constant based off of the surface area of the ball times the velocity of the ball squared. The observed motion of this, for the observed motion, we had the mass of a napkin, which was 28 kilograms, and we had the initial velocity, which was 0, the initial position, which was also 0, and for this we had the positive direction being up. So everything in our lab is going to be shown in a negative direction. And as we see distance versus time, it's a slightly increasing, not very much, but just slightly increasing position versus time graph, or I guess decreasing, since it's negative. Or increasingly negative, sorry. And then velocity time graph, it shows a slightly increasing velocity over time. Observed observations, comparing between no drag and drag for the position versus time. Without drag, it continues to increase in the negative direction, and in position versus time with drag, it starts to straighten up and does not seem to have any acceleration towards the end, which is very much shown in the velocity versus time graph, where we have a straight constant negative velocity without drag, and with drag it actually flattens out because we achieve something called terminal velocity, which is where the drag force is equal to the gravitational force, and it leaves us an acceleration of 0. Our code, for our code, we used, for the force of gravity, found the mass of the ball times gravity times the second scalar of the vector of j hat. And for the drag force, we had B times the second scalar of the ball's velocity squared, which is the y coordinate. And the FNet was combining those two together. And then we use the update formulas, both the position and velocity, with to iterate this through the code, iterate the points through the code. And observed versus predicted. As you can see, the predicted without drag kind of veered away from the observed and predicted, and that's because there was no drag force holding it back and slowing it down. So it continued to accelerate, unlike the predicted and observed. The observed and predicted were very similar in the position versus time, but however, in the velocity versus time, the observed force starts off at -2 meters per second, unlike the other two. And then, but it continues continues the same path as the predicted one, and the predicted without drag goes in a straight line because there is no drag force to make it reach terminal velocity, which is what it reaches around in the observed around 2.4 meters per second, and the predicted in around 2.3 meters per second. And that's because the net force equals 0 and there's no more acceleration there. And some of the errors, the ball the ball was spinning in the air, or the paper napkin ball was spinning in the air, and that might be because there was so that could attribute to surface changes, which causes slight changes in the drag force, and then which is why it spun a little bit and kind of went in the x direction a little bit. And then the initial velocity not being 0 is probably basically we could have had initial velocity of like around -1.8 meters per second, and that would have attributed to on the right the big gap in difference. Question: if the ball object was initially thrown downward, it would not change the terminal velocity of the object. The drag force if the drag force was, if the ball went past terminal velocity in terms of speed, drag force would be greater than the gravitational force, and then it would decelerate back to terminal velocity again. If it was still under terminal velocity, it would continue to accelerate till it reached terminal velocity. And that is it. Thank you all.